Now it's time for the explanation, where I explain everything that happened and reveal to you which balloon truly popped the slowest and why that happened. So, to begin with, air popped in precisely 2.3 seconds. Not very cool for air. But why did that happen? Well, I will explain it. What's new? Scooby-Doo Volume 3. This is going to act as our fire, but you're probably confused, so let's get into it a little. Specific heat capacity is described as the measurement of energy required to raise the temperature of 1 kilogram of material by 1 degree Celsius. So basically, how much energy is needed to change the temperature of an object to bring it up. So basically, that's about it. For example, fire, how much energy that is producing to change the temperature of an object would be specific heat capacity. So, the balloon is just composed of rubber with air inside. Rubber has a specific heat capacity of 1600 joules per kilogram degrees Celsius of energy. And what that means is that this is going to be our fire. Scooby-Doo, Volume 3, What's New Scooby-Doo? We need our balloon with air inside. No, not that one. Let's see. Alright. What's New Scooby-Doo, the complete season, first 13 episodes across 2 discs. This is our balloon with air. Fire. Burning. The candle. Transferring thermal energy into this rubber balloon right here. Now it's a very low specific heat capacity, so not a lot of thermal energy is required to raise its temperature. So every 1600 joules per kilogram degrees Celsius of thermal energy that enter this rubber balloon increase its temperature by 1 degree Celsius. And it has a very low melting point of 120 degrees Celsius. So the candle burns, this heats up very quick, and after only a little while, it begins to melt, a hole forms, and it pops. 2.3 seconds of that. Very fast, but this is a big spoon. Doesn't have to do with the video. Alright. Let's see. Scooby-Doo and the Loch Ness Monster. Classic. What's New Scooby-Doo, Volume 1. Space Ape at the Cape. That's this guy. That's Shaggy. That's Scooby. This is a full-length movie. But that's not important. You didn't come here to see this. You didn't have a choice. So, fire, candle, hot. This is our balloon. It has water in it though, 25 milliliters. And that 25 milliliters of water is also known as Scooby-Doo's Greatest Mysteries. Water's in the balloon now. Here we are, very accurate demonstration. Candle's hot, but water has a very high specific heat capacity of 1400 joules per kilogram degrees Celsius. Very high, so which means that when heated, it heats up by a degree Celsius very slowly. Water's at the bottom, thermal energy from the fire going into the water. Going into the water, and since the water's absorbing all the thermal energy, it has to transfer that thermal energy into the balloon. Because of that, so this heats up, this rises slowly, and this transfers thermal energy into this, also causing this to rise slowly. So because this rises slowly, this cannot gain more heat than this is giving it. So if heat in this rises slowly, heat in this rises slowly, which means that this will reach, well, the boiling point for water is 100 degrees Celsius. So we're going to go with that, which means if this takes a long time to reach 100 degrees, then this will take a long time to reach 100 degrees Celsius, which means that the balloon will take a lot longer to pop. And our 25 milliliter cup of balloon water took 1 minute and 30 seconds. 50 milliliters of water, I'm gonna say straight up, was a shock. I did not expect it. It popped in 44 seconds. 44.7 seconds. And I hate to say this, that's not what was supposed to happen. It was supposed to last like 7 minutes. Because that's how science works. And I will explain why. But my theory is that a couple of variables, which I had not accounted for, I actually don't know, but caused the balloon to explode early. What was supposed to happen, I stated, it lasts a lot longer than the 25 milliliter balloon. This orange right here, love oranges, delicious. This orange is a balloon, let's say, and my hands are the heat. I peel it, and I'm using a good bit of energy, so the water is ready, like the water amount and the energy being produced are about the same, so it's heating up. So it's heating up pretty quick, the water inside, but still peeling the orange. I'm not gonna peel the whole thing. So, peeling it, energy matches, like this orange is small, and I'm peeling it, I'm using a fair bit of energy, but let's say this orange was big, really big, equivalent to, if this, 25 milliliters, about 2 times this size. But I'm still using the same amount of energy that I used peeling this one to try and peel the big one. So obviously it's gonna take a lot longer to peel that big one. And that is pretty much the same thing. There's a lot more water, a lot more atoms to give thermal energy to. A lot more atoms to give thermal energy to, so it takes a lot longer to heat up. Because the candle is still giving the same amount of energy to the water in the balloon, but it's more water, so it takes more time. Simple. But if you want a little explanation, I'll give you a quick formula. Q equals MC triangle T. Q is energy, M is mass, C is specific heat capacity, and triangle T is change in temperature. So, if you increase the volume of the water, that means increasing the mass. And if you increase the mass, the energy is also going to increase. And since energy also relates to time, the time is going to increase. Simple as that. But I hope this isn't very interesting for you, so let's get real. Cold water. The cold water, that was a specimen of beauty. 25 milliliters of cold water, the others were room temperature, lasted a full 6 minutes and 30 seconds. So I bet you're wondering, why did that happen? Well, let's get down to it. Shrek. We all know it. We all love it. I don't need to say any more. So this is our fire, not with the metaphor. Fire. Heating our balloon, but it's filled with cold water. Let's say the cold water is real cold. Like I just melted ice. It's negative 200 degrees Celsius, metaphorically. Real cold. If you walk into it, you will die. Very cold. But fire warms it. Specific heat capacity slowly increases the temperature until it reaches 100 degrees Celsius. So obviously, because, once again, the specific heat capacity of water is very high, it's going to take a long time, but because it has to go, like, let's say the 25 milliliters room temperature was 0 degrees, they only had to rise by 100 degrees. But theoretically, that is, this is not accurate. Well, it is accurate. It's theoretical situation right here. This had to rise by 300 degrees. So you can get why it would take a lot longer.